So, okay, I think we are ready to start. Thanks, first of all, thanks for evaluation. We are quite happy with that. Thanks a lot. We still know that there are some rough edges that we need to improve for the next iteration, but I think we're quite happy, and I like that you are quite happy with the course. So therefore, today we will start light, and then we dive very deep into the math, so to see how we can use reinforced learning. That would be a topic for today's lecture, reinforced learning. And originally, if you remember the first lecture, I mentioned that I don't want to give you reinforced learning, since it's less applied for the mechanics and more probably applied for the control theory, for the autonomous vehicles, or all these fancy things. But I realized that it's quite interesting topic, and today you will see why. And on practice, this Thursday, we will play a little bit with reinforced learning models, and we train some simple models to sort of compete in the real environment and to execute some tasks by learning from the environment. So we will start again, as usual, with recap. Let me just do that. What have we learned previously? We studied for two lectures. We studied the problem of generation and considered different generative architectures. We learned about variational autoencoders and even implement one during the practice session. We know that they can be distinguished by the bottleneck between encoder and decoder stages of the model. So that's one of the trick how you can immediately see the variational autoencoder or autoencoder in general. You have this encoder part, you have decoder part, and some bottleneck between them. We'll also get a little bit familiar with GANs, architectures built on the competition between generator and discriminator. And this is quite powerful idea in generally to compete between two models, and even in reinforced learning, and I would say in reinforcement learning in particular, it's very, very common idea. Finally, we discussed a bit state-of-the-art diffusion models that enable us to generate a very high-quality images with a quite diverse range. And finally, we discussed the application of such models in the mechanical engineering and material science on an example of a couple of manuscripts. So, and today, again, as I mentioned, we will start something new. So what have we done until now? We worked with datasets. So this is one very familiar for you data set. It's MNIST. So we have this digits in MNIST. Again, we have data sets of cats. I like it. So we also can train models to distinguish cats from dogs or doing something similar. But there is a question, where do we get such data sets? So of course, like the simple answer is from internet. But in general, conceptually, if we think about that, we already should, before training neural network, should have quite a lot of data. And we actually even need to have the labeled data in many cases. So if we want to do classification or regression, we cannot avoid talking about labeled data. And in some cases, it's really hard to get that. So if we don't have data set immediately, then maybe the classical deep learning would not be an optimal solution. So, and what would be the optimal solution? In this case, we can have two different options. One is called active learning. And in this case, what we have quite big design space, quite big amount of data. And what we are trying to do, we try to effectively label this data. So for instance, if you have the image of, I don't know, number 4 that looks like that, and in your data set, and you already know that it's already labeled, so you have label 4, and then you have image of like that, very, very similar, so no difference almost between this one. It would be quite honestly stupid to I don't know, hire someone or to ask someone to label this one as well. So the question of the labeling is always the problem in who is doing that, who is doing labeling. If we assume the computer cannot do labeling because we are before this training stage, that means that someone needs to spend time on that. And in this case, it probably would be not very smart to do labeling. Or let's say we have 100 images of cats and 2 images of dogs. And now, what would be the and we would like to distinguish cats and dogs. And let's forget about this anomaly detection and something like that. Let's just talk about classification problem. So, and I get another picture. What should I actually, like, I have another 50 pictures of dogs and pictures of cats, and I actually haven't classified yet. So what I would like to label next, which picture? So I would like to separate, I would like to distinguish cats and dogs, yes, in the classification, not talking about autoencoder system. And right now I already manually, I just sat over the evening, like look at the photos and say, okay, this is a cat, this is a cat, this is a cat. And what I had 100 images of cats. So right now I have 100 elements from my data set with the label cat, and I have only 2 with the label dog. But I still have 1,000 more pictures. So what would be logical to do next? Should I label more cats? No. I would probably prefer to label more dogs in order to get this variety, in order to allow the model to distinguish them better. So therefore, there is some sort of selection process in the labeling. And that's called active learning in this case. So we have a quite big design space that we can access, but we need to be smart. We would like to train our models using as small amount of data as possible, because labeling can be quite expensive, both computationally or maybe in some case money-wise. So, and as alternative, not alternative actually, it's a very different domain. We have reinforced learning. We have no labels and rely only on feedback from the environment to assess the goodness of our model. So there is no labeling involved. We just try to understand how environment works, or we would like to create the model that will be able to utilize this environment to achieve specific goals. It's a very different concept. Don't mix them because they're quite often mixed. And just to give you a little bit of examples of active learning, this is a project that we are doing together with Roy. He right now is master student in the lab. And the project is very simple. So what we have here is so-called waveguide. Of course, it's made not ideally. In ideal cases, what you do have, it's like so-called impedance tube. But we, on purpose, did it as cheap as possible. So what we have right now, here we have so-called rotators, then can rotate on the angle from 0 to 100 degrees, something like that. What happens next, if you look at this side, what you will see loudspeaker. So we generate acoustic waves, so sine wave in general, let's say on the frequency of 4 kilohertz. And what we have here, it's actually a microphone. And of course, we kind of intuitively can understand when sound starts to propagate through the structure or anywhere, it starts to reflect from the scatters in this case, or from the walls of this channel. And therefore, what we measure in the microphone might be actually not so loud. No, come on, really? Might be not so loud in comparison with what we generate. So if we have an empty waveguide, we generate 5 kilohertz with amplitude, let's say, of 1 decibel or whatever. It's actually not exactly correct. So with some specific amplitude and we measure what's happening, we see the same amplitude. But if we have some structure inside, our sound waves start to interact with the structure, and therefore we can measure the attenuation due to the structure interaction. And that's what we are doing. And now the question, what would be the optimal angles for all these 6 rotators that will attenuate our sound in the maximal value? So we would like to say, let's say, have noise reduction. Garrett, what's happening with it again? I think you told me that you fixed it. Oh, come on. We can give it a try. If it will really be annoying, we can give it a try. I think it's also heat affects that. So what's happening, we would like to find a position of these rotators to get the maximal attenuation, so reduce the noise. So, and what's happening, we can run this system autonomously. Please run. Hey. Okay, so you see, how it's not right. But what's happening actually, it's autonomously just rotate them, and the amplitude of rotation getting smaller and smaller because what's happening, we're solving optimization problem. At the beginning, in a random position, we have something around its relative units, 1000. And after 250 probes, so we probe different positions, we get attenuation around 50. So we actually are much better in reducing the noise in this case. And the final position, actually optimal position here is quite clear. It's just these rotators. Everything is 90 degrees. And that's cool. But this is what's so-called optimization. We are using here a black box optimization method. Very simple, the basic one. So yeah, and oh, it started to move. I have no idea what's happening with this computer, with this projector. So it will be a mystery for us. This is an optimization problem. It's quite interesting. But what if we want to know relation between angles and transmissions? We are not looking for the minima. Right now, we, let's say, want specific attenuation. What should I use as my angles in order to get this attenuation? That's ridiculous. And here, do you think it's? Do you think it's there? Do you think it's really there? It's very annoying. Can you check it in this case while I'm telling the stories? Take this chairs or whatever. What did you do? Okay, let's again. That's so. What we are doing right now, while Gerrit is trying to fix it, I hope it will work. What we can pose the question in the following manner: how these angles related to the propagation, and this is what Roy is doing in a lab. So in this case, it's a differently structure. It's these rotating elements, and we're rotating them, and we probe different positions, and build a model that will tell us the relation between angles and the transmission values. And we see that it's kind of probing not randomly, it's try to probe in the positions when it's not certain about the model. And at the end, after a couple of iterations, our variance actually goes down, and we are quite good, this blue line, into the real prediction. So right now we have the... Come on. Do that if you can. I will be not against. I really want it to work. So yeah, at the end you see very nice model. So while Gerrit is doing that, so this is active learning. So here what we have this our design space, and we are trying to probe the behavior and build a model. I can do that probably because I'm taller than you. Which one? This one? But this is internet, no? It's clicked. So I hope if it's clicked, that means that it's good. So, okay, that's active learning. But we will talk about reinforced learning. And we should understand, honestly, this is quite hard to condense everything to one lecture, but we need to do that. So reinforced learning is an extremely mathematically heavy topic, much more, in my opinion. In the previous case, your data is the angles, and your labels. Okay, your data is angles, and your label is transmission coefficient. So how much sound is actually attenuated or reflected. So just one value. You can do it a little bit in a more strong formulation, but nevertheless, it's not a topic right now. So reinforced learning, extremely mathematically heavy topic, and if you are interested in that, This is a couple of courses for winter only, and I think Professor Moritz Diehl is responsible. And by looking actually at that, have you met Professor Moritz Diehl? You know, so what he is teaching is optimization and control. So reinforced learning, it's more closer to the control theory rather to what we did with the deep learning. So again, if you're interested in that, this is a lecture that I probably highly recommend. But what we will do here, we will just give a basics and some math behind that. So reinforced learning, we have no labels and rely on the feedback from the environment to assess the goodness of the model. This is the main idea of the reinforced learning. What we have there originally is an agent. Agent is our entity that tries to learn how to act in order to be successful. So what agent can do, it can, first of all, it exists in some specific state. So we'll go back to that. So right now we have agent, and it can perform some action. So it performs action, and depending on this action, our environment gives him the next state. So for instance, if I say I'm standing here, my action can be I do a step right. So now environment will tell me my coordinate, for instance, it will be my new state, and also can give me and needs to give me reward. So how good I am, how good this motion was from the point of view of environment. And then this state and this reward gets back. So our agent right now is in another state, and he can perform some action that will go to the environment. Environment will give some reward and move him to the another state, and so on. So again, this is very simple to see on examples. Okay, we have, let's say, squares, and we have 2 coins here. I don't know, $2, $3. We get some, I don't know, burglar here that will give us minus $100. And now we're in this state, and what we can do, this is a state. And what we can do, we have 2 actions, let's say. We can go left and we can go right. So if we go left, which state we will go from this? From this state, we will go to this state, right? So we right now will be existing in this state, and for that we will get $2 reward just by moving here. In other actions that we can take, we can go right. Yeah, right from this point of view. And in this case, our action would be go right, and what we will get as a reward, we will get minus $100 because we will be robbed by some not very nice guy. So do you see very basic logic behind that? So you have a states, and between states you can move using the actions, and depending on this transition you get different rewards. Come again? Okay, exactly. So for instance, there is a classical problem that you will be able to solve during the practice. It's called mountain car. So this is a car, and this is the mountain, and the goal is to reach this so-called terminal state, so to reach the flag. Car can accept only 2 actions, move left or move right. So what, in your opinion, would be the states of this card in this case? What we will describe as a state? Any ideas? So actions, move right or left. States. What? Come again? Oh, it's MJ. We are not considering, like, there is a physics, of course, in this environment. We don't know about that. We just, what we can do right now is sort of blindly move and see what we'll get. So states, in this case, I will give you a hint. Very close. X coordinate, Y coordinate will be calculated automatically by environment. You cannot be here, for instance. You will be always. So we have X coordinate as our state variable, and another one. Exactly. And a velocity, because you can be in the same position but with different velocities. That would be 2 parameters. That will be 2 states. And of course, sometimes we consider continuous states, but you can also do discretization. And now, for sort of what, for instance, I will give you a hint. Let's say this is a position 0, and we have position 0, 0. This is our state 0. And like right now, I would like to apply action go left. So what would be my state 1 after this action? Again, minus something, yes, I would guess, maybe let's say minus 1. And the speed will be, if we take into account some accelerations, we don't know, environment will provide us with this data, something like a speed. You see how it works? So we have a specific states, we have actions, and actions allows us to move there. In this case, we are quite deterministic. There is no randomness. So sometimes you can include randomness. So let's say you try to move left, but I don't know, it doesn't work. But in this case, it works. And the task that you will solve, this car has limited engine power. So if you will try to move right, you will never reach the top of the hill because gravity will prohibit it. So in this particular problem, the goal is to find the optimal transition between states and actions that will allow you to climb here. And of course, you already can see which one will be the optimal. If you just drive right, you will never be able to reach the flag because your car is not so powerful. Any ideas how to reach the flag? Exactly. So actually, the optimal strategy in this case would be to go left first to get some speed, and then to get some potential energy and go here. And that's your agent should learn just by taking the response from the output from the environment. That's another example, labyrinth. So let's say you start here, yeah, and your task is to get the terminal state here. And why reward is important? Reward is important because, technically speaking, if you have no reward, you can just go through this labyrinth, whatever you want, and finally reach this terminal state. But as a reward, in many cases, you have a penalty. So instead of giving your points, for each step, I will subtract 1. So therefore, if you will go along this path, you will lose a lot of points. So in this case, the optimal solution, the solution that we are aiming, would be a solution that reach the terminal state with a minimal amount of steps. So, and in this case, question, what is the state of my agent? What I can describe as a state? If you're playing this game, just find the exit. What is the state? How many states do we have? Why 1? No. Okay, what actions do we have? How many actions do we have? Actually 4, yes. For instance, here we have a 3 because we 2 actually, but in general we have 4 actions. We can go right, left, up, and down. In some cases we will be penalized because we hit some border, but in general we have 4 actions, right? Up, right, left, down. What is a state? Actions should transit us from state to state. What in this case we can describe as a state? Exactly. So we have 25 positions. Again, maybe some of them are not achievable, but state is a coordinate, or the number of our square we are right now. Clear? So that's a state. So we have 25 states, and one of them is terminal. So terminal means that we will end our so-called trajectory episode. That's another example, Pac-Man. It's a very cool game to play with reinforced learning. What would you consider actions here? How many actions do we have for the Pac-Man? 4. Again, right, left, whatever. What would you consider as the state of the game? How many states in this case we will have? 3. What do you mean points? But we have so many foods here. so much food. How you can describe this food in 3 only states? Yeah, and? No, velocity doesn't matter in this case. What number? Oh, okay. Yes, it's kind of not exactly the state, honestly, but it's something similar. But I have a question. So states should be quite unique. So in order to, you shouldn't have the same state describing 2 different states of the game. So now my question, if you're doing that, what if I will just remove this particular thing here? Will it be another state? I will remove this food from the game. It will be another state. For the game, it will be absolutely another state because there is no food anymore here. So in this case, our states actually the images of game. So all possible images that are kind of allowed in the game. In this case, we can maybe split it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 20 by 10. So actually our state is 20 by 10 array. And each of this array will describe only one particular state, and every state can be described by this array. So, and in each position of this array, you say, okay, if there is a food, we say 1. If there is a Pac-Man, we say 2. If there is a ghost, we say 3 or 4, depending on the color. If there is a wall, we say 5. So you see, that would be enough to describe our game. If we will avoid talking about that, we cannot distinguish some of the states. So if we forget about, let's say, red ghost, we have a problem, because then we will try to solve this game, and Pac-Man will have absolutely no idea where the ghost is. So that's important. In this case, we have a quite large state space. And that's why classical reinforced learning that we will see, Q-learning, will have a problem with this because it's very massive. There is a very good example. Did you switch it off? Sound? I think you switched it off. This OpenAI, the guys who did all this fancy ChatGPT and stuff, before that, they did a very interesting research. I will rerun it, sorry. Okay, is it loud enough? It's 3 minutes, very cool thing.
The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who learn to use tools. After many generations of failing to break into shelter, the seekers learn to jump over obstacles using grass. However, after many millions of rounds of having the shelter breached, the hiders learn to take the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors, as each team learns a new skill that implicitly changes the challenge the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing objects, team sizes, and walls. In this way, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy for agents learning. However, we found that after more training, the seekers discovered that they could jump on top of boxes and surf them to the hider's shelter. In the last stage of the emergent strategy, the hiders learned to lock as many boxes as they can before constructing the fort in order to defend against box. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other, as well as past versions of themselves, using an algorithm called self-play. Co-evolution and competition on Earth led to the only genetically intelligent species known today, humans. While this world is far less complex than Earth, we have found that simple rules that make the perceived intelligence of multiplication compassion. We hope that with a much larger, more diverse environment, truly complex and intelligent beings will one day emerge.
So that's how you can use reinforcement learning. Sorry, I pronounce it wrong every time. To train these agents. And two things that were actually mentioned here, it's competing one against other. So they're competing, and this is something similar to GANs. It's a very useful tool in general for training. And another thing that actually they mentioned is self-play. And this is the same team. No, it's DeepMind. Who want to go? DeepMind? Yeah, DeepMind. It's another team. They basically designed this AlphaGo system that beat the world champion and right now dominate the Go scene if they are playing. So I think this particular engine already retired, but there is a very cool, quite long movie regarding the development and playing against Lee Sedol, I think his name, champion. And again, they used a very cool approach how to train this neural network. This reinforced network, actually played against previous versions of itself. So it's getting a little bit better, and then it's playing against a little bit older version. And then again, it's getting better and playing it. And it's constant improvement. It's self-play. In this case, it's playing against itself. And it helps to achieve something that was sort of impossible for the computer engines. So yeah, that's a fun part. Now we need to go a little bit deep in terms how does it work in general. So we have the system, agent, action, environment, and state and reward. So states, we already discussed what is state. So they usually consider to be, let me just use normal pen. So states are picked from specific set of possible sets of possible states. So we know that in this maze game that I showed you, 25 states, and each state belongs to this set. Then we have an action, and in this case, action is actually element of another set that depends on the state. It depends on the current state S. Do you understand why we cannot say that action is just a part of the some set? Why we need to add these brackets? Any ideas? Let's use the example of the maze. Do all states have the same set of actions? No, because in the corners, for instance, we cannot move down and left. So therefore, these actions can be picked only among specific set of actions. And finally, what we have the reward. Reward is actually, again, let's make it small. Reward is the element of another set, and this is subset of some rational number. So usually, as rewards, you can think -1, 0, 1, or whatever combination that you want. So you either penalize, you do nothing, or you give the reward. So, and in order to describe the environment, what we do, we define this probability function. It's maybe hard to see, but what's happening here, let's take a look at on the right side. This is actually just the probability to move to another set S prime and get the reward R, considering that right now we in a state S and we perform the action A. It's very, very simple. So T, you can treat T as the time. So let's say at the time equal to, we're in specific state. If we have, let's say, this one-dimensional maze, so let's say we in this state, it's our state S. So now we can move either right or left, or we can actually jump over some states if we're and therefore what this probability function describes is the probability to, let's say, appear in this particular state, assuming that we start from here and take the action A. So let's take action left. So you can treat it as, let's say, we have a 50% probability to go here with this action, or accidentally we have a 50% probability to just jump over 2. So do you understand that by just knowing this function, this is a shorter form, we describe everything. We describe all transitions between all states and what rewards do we have for that. So that's this probability distribution plus set S plus set R and A defines so-called finite Markov decision process. There is one trick. What we assume here, we assume that history doesn't matter. It's very important assumptions here. So we don't know how we reach the state S. We don't care about that. We just look at the state S. We look at the action A. This is our conditioning. And we tell what the probability to appear in another state and get reward are. Conceptually, is it clear? Again, this is quite mathematically maybe scary, but it's super, super simple. Yeah. That's the thing. You will see what it can return back. It kind of you can stay at the same position. For instance, there is also, if you put S, there is still, you can derive some probability and it will be there. So it's not prohibited. It's just to describe environment itself, like what would be the penalty and what would be the rewards or according to specific actions. So history, it means that it doesn't know the previous states. It doesn't use the previous states to decide on the next one. So it right now can look only on the current state and move from there. It still knows about the previous steps, but it doesn't utilize it into the selection of the next action. So that's important. Again, you're absolutely right. It's not forgetting everything. That's exactly why reinforced learning can work, because you still get data. Still data exists. It's not forgotten, but you do not use this data directly to make decision on next action. So that's what I mean when I say there is no history. You will, again, right now, we are not talking about memory at all. You will see in an equation in the next basically slide, so-called discount factor. And again, you will see. So right now, it have been in some specific state. It's moved to another state according to this rule. So this rule actually defines, together with the sets, whole environment. That's what's important. And in this environment, we will do this chain selections of the next states. So what's important in this case, how we select an action, how we understand what to do. And for that, in reinforcement learning, there is a special term, policy. And policy is described like that. It's pi. It's a probability, again, to select action A, considering that you are in the state S. So what does it mean? For instance, you have your grid. Let's say, again, and you are here. You cannot move diagonally. One of the policies that you can take, let's say P of action will be equal. So probability to go right would be equal to 25. Probability to go left, down, and up will be absolutely equivalent. So in this case, what does it mean? It's like, okay, our agent in this particular state will randomly go right, up, left, or down. That's a policy. In some cases, in many cases, in deterministic cases, you can write it like that. What does it mean? It means that you know exactly which action the agent will take the specific action in this state. So it will always, for instance, for state like that, it will always move right. So there is 100% probability to move right, and therefore instead of doing probability, this conditional probability, what you can say that your action is just sort of function of your state. There is no choice anymore. There is just specific. If your app or if your agent in this state, it will move right. That's the idea of the policy. Okay. Now, what is the return? And you'll first time see here there is R, and R is a reward. So for each action, we know between states we can get reward. Again, in some cases it's penalty. So technically speaking, we can create a system that, let's say, have states, and you move always right. And for each of this motion or movement, you get reward equal to 1. And in this case, when you will reach the terminal state, you will get total reward equal to 5. And that will be exactly the return that we're calculating if you assume that this value is equal to 1. So you see it just will be a sum over the each transition reward. Why this value is here? It's value between 0 and 1 that is called discount. This value is important because if you look at that, you see if you're in the step t, well, let's put k equal to let's put t equals 0. We're just starting. We right now didn't do anything. So what in this case will happen? Okay, we'll do it here. In this case, our reward for the state would be the sum of the previous states, and we have no previous states. Therefore, we cannot use this state t equal 0. Okay, let's take t equal 2. So now let's see what would be the return at this time equal 2. In this case, we will have sum from 1 to 2 of this function, and k minus 1 minus t minus 3, sorry, rk. So what we will actually have, I'm not sure if actually my math is correct here, 2, t is 2, 2 minus 1, minus 3. Okay, so our G2, our return, would be something like that. I think it's, in this case, it's minus 2, right? No, it's there. So what does it mean? It means that return from the previous step, since this value is between 0 and 1, the return here, I'm not sure that I'm doing correctly. No, I'm doing it incorrectly. Sorry, what I'm doing. T plus 1 minus t minus 1 is equal to 1. Okay, t is equal to 2. For 2 plus 1, 3 minus 2. Oh, okay, yes, of course, sorry. My math skills are getting worse and worse. So let's again. We assume that t equal to 2. Therefore, we are going from 3, right, to some terminal state. Let's say t. So what we're, in this case, are doing, it's taking this value, okay, k minus 3, that's fine, r k. Okay, so now let me, I don't want to write here. Let me delete this thing here. I think it's, so again, we have g t2 equal to sum from 3 to some terminal state t. Let's say it's somewhere in the future. Let's say 10. After 10 stops, we will after 10 steps we will stop counting on this value chi minus 3 r k. So if I will right now open the summation sign, what I will get in 0 R3 plus O5. You see? Are you agree with me that what will happen? And therefore, what is R3, R4, and R5? It's a future rewards. It's a rewards that I will get in the future. And therefore, if I will put some factor that is between 0 and 1, I start to discount the future rewards. So right now, when I will select something, I will focus more on the immediate reward rather for long-term reward. So in many cases, what's happening, you assume this gamma factor is equal to 1. In this case, for instance, for the maze. If you want to go through the maze and get it as fast as possible, you penalize each step without discount. In other cases, you want this discount in order to plan for the future, because your future reward may be not so important for the strategy as a current reward. So this is called discount factor, and in almost all cases that we will consider it will be equal to 1. But this is how you separate between the rewards immediately after your action and rewards that may be in the future if you continue to execute your so-called episode. So you will go from state to state. Is it more or less clear? It's not so important, but in general, it's a way to sort of separate immediate and long-term rewards. And finally, what's actually we are doing in general? Oh, I had a place to write, but okay. We just want, our goal is to maximize the expectation, again, this is from statistics, expectation of our reward, of our return, assuming policy pi. That's a thing. With the policy pi, with the specific policy that we have, we would like to get as much, I don't know, points, bonuses in return. So that's whole task of reinforcement learning, to maximize this value. You will see how we can make it a little bit easier on examples. Clear? At least. So now let's take a look at the very simple system. We have two states. We have a square and we have, this is a states. And we have two actions. It doesn't mean that let's not consider that a square at the left of the circle. It's not the case. Imagine that you have a situation when you have a screen, and on a screen you can either see the square or circle, and then you have just two buttons, left and right, and you're just playing left and right, and that would be your system. You have two states and two actions. Now, what I can provide you, I can provide you this. Remember, we're talking that we want to have this P that would be S prime reward, assuming S and I. So this is one of the way how I can do that. So first of all, let's consider our initial state to be square, this one. From this square, I can have different rewards, and I can go to the different states, and that's my rewards. And this is my states. So again, I just write it again here, just for you. And I will do that with a different color. And so now this is blue. And green one. And this is green. So right now I am in the state S, and I can take action. What action I take in? I take in the action right. So if I will do that, if I see the green square and I press right, this table gives me all information of what happens next. With the probability 0.4, I will get -1 as a reward, and I will move to the circle. With the probability 0.1, I will remain a square, but I still get a penalty. And there is, again, probability 0.3, I will get plus reward and still be a square. And with the probability 0.2, I will get reward and move to circle. That's That describes what's happened when I press right in a green square. Is it enough to describe my game? Tell me again. No, I don't. Right now, I don't put yet to get the maximum reward. I just need. Okay, yeah. The goal of the game is to get maximum reward after 10 iterations. Is it enough to describe my game? How many tables do we need actually? What do you mean where these are? What do you mean? No, we don't consider like the geometrical movement on the screen. We just look at the screen, and screen shows us either square or circle. And we have two buttons. Again, here it's called left and right, but I can say A and B buttons. I just press A and B. And I would like to describe whole environment. I would describe everything, this probability that we introduce. And for instance, if I start with a with a square, and I press right, that's my table. That's what I will get. Is it enough to describe, or we need to add more tables? Think. It's easier. Okay, what would be next step? Okay, I press right click, and I with the probability went here. I get penalty, and right now I see the red circle on my screen. You see a problem? Right now I have no idea. The environment will give me nothing. I can press right, but I have no probability distribution anymore. That means that my system is not described completely. So what actually I need 3 more tables. I need 3 more tables. One of this table will have the circle at the. I don't want it to be. It will be red. We'll have a circle, and let's say right motion, and I will absolutely the same table, right? Another table will have what will happen if I will press left from the square. And finally, table would be if I'm right now in the state of the circle and I press left. Do you see it? Do you see that with that, if I have 4 tables, I can do whatever actions I want. I move from states to states with some rewards, and it's exactly complete formulation. See? I hope you see that. These tables will be important in general. So that's how we can define our problem. And from here, it's a little bit hard to work with this probability. What you can get is, and this is extremely important, it's one of the fundamental aspects of reinforcement learning, is so-called state value function and action value function. So what we can say, let's say that we have the policy pi, according to which we make a decision depending what to do, depending on the state we are, right? And let's just say that now our, remember this sort of return that we considered. Right now, just compute the expectation of this return, considering that we are in the state S. So for each state, we're saying how much more points we will have on average, because it's expectation, if we start from this state. It's very simple. It's like really very, very simple. And there is another way to do that. Let's say we have a so-called action value function. So right now we depend not only on a state, but also on an action. And that's a probability, it's expectation to get of the reward that we are, not total reward return in this case it's called, if we in the state S and we decided to do a state A, to action A. So let's say we in the state square and decided to move right. For this particular point, we can calculate for this particular state and action pair, we can calculate our expected outcome, our expected return. It's a very simple idea. Do you see it? So for each particular state, let's say square or circle, we can run multiple, let's say, simulations, multiple passes, it's called episodes, and get this average reward at the end. And we just say, okay, now this number belongs to the state, or this number belongs to the state and action pair. So it's just very simple. It's like as simple as can be. In this case, what we can say, I think in this case I will show you some trajectories. Let me go back a little bit here. So what is trajectory and what is episode? So let's say that we start with the. I will do it black because I don't want to change it. Let's say that we start with the square, and we take an action right, square, and right, and now by some random sampling, what we get, we go +1, and we get circle. It's one trajectory, it's one possibility. Then we take a circle, look at one of these tables on the right, and say, okay, now let's say my action will be go left. I press left, and maybe I will get reward -1. I don't know. There is some table here. So I get reward -1, and now I'm again in circle. So I press again. This time, by probability sampling, I will get some sort of +1 reward. And let's say I get to the square. This is, and at some point, I reach terminal state, so-called. Again, it's we can say we stop after 10 cycles, or we can say some of the states, like in maze, the final square, it's the terminal. We stop our game. In this case, what we stop our episode. This is called episode. And this line, it's called trajectory. Now we can repeat it. We can start even with the same square and even take the same action. But now, by random chance, because we have this table, we can get a penalty and keep in the square. And we continue doing that, and we have another trajectory, and another trajectory, and another trajectory. So we have multiple trajectories for these episodes, and when we go back to these definitions, this is sort of averaging on all trajectories. This is averaging of all trajectories. The state value function and action value function, it's just averaging on from the state that you are right now for the action that you select. This is averaging of your reward. Because in this case, you calculate +1, I see, +1, -1, +1. So you have a 1 as your reward. Here you have -1, let's say -1, -1. You have a -3 reward, and so on. Yeah. Come again? In this case, we don't have a terminal in this particular game. Yeah, we can limit amount. In this case, let's say I stop everything after 3 moves. So it will be considered as terminal state. But in general, as a terminal state, you consider some sort of, again, you reach specific state. Usually it's called terminal state in this case. Again, you solve the maze, you find the exit. Or I don't know, there is some different criteria how to stop. If we continue it infinitely, that's a very different theory. It's absolutely different approach. Surprisingly, it works only for finite Markov processes. So, and in this case, what we want, so we have a state values and we have action values, and we know that they're actually connected to how much things we get at the end, how much reward. And now we can introduce optimal policy, because right now in each state we can our agent can say right or left, press right button or press left button, and our optimal policy is actually. How to simplify it? Is to say that for the optimal policy that we select, for each state, we should be optimal. Or, another way to say that, what does it mean to have the optimal policy? It means that our state value functions for every state and every other policy that you select will be maximal. Or our action value function for this policy would be always, for all states, all policies and all actions will be the maximal one. It's kind of, that means that you cannot come up with another strategy, with another policy that will be better. So for instance, again, let's take a look at the game like that. And let's say this is a terminal state. And each step gives me a penalty -1. And now, right now, I'm in the state here. What would be the optimal policy for this state? Move right or left? Each step I getting penalty. So therefore, I don't want to have a lot of penalties. And I want to reach terminal state, because terminal state will give me +10. This terminal state will give me a reward +10. I'm right now in the state with a dot. Where should I move? Right, exactly. So what if I will in this state? Where should I move, left or right? Right, again. So what I will get, if I will then calculate the penalties, so here I will have -1 penalty because I moved. Here I will have -2. I'll say -3, I will not consider this one, right? So this is a policy. Right now, what we describe, it's a policy. We described P star, in this case, we clearly see that it's optimal. There is no other way, but we describe the policy that say, for S, always pick this one. So action is always right. So now let's imagine I have another policy that we call P2, and this policy would be 50-50. 50% time I go left, 50% right, I go right. In this case, what will happen here? It will definitely be not optimal policy. If I will then calculate my expected, so where these numbers -1, -2, and -3 come from? Because under this policy, this would be exactly state values. Exactly my expected reward considering this policy. If I'm always moving right, I will always get this reward, -1. If right now I will consider 50-50, you can see that it's expected that I will have more steps on average, and therefore my final return would be lower. So that's policy is not optimal, and that actually will mean that all these numbers would be much lower. It would be -10 or something like that, and therefore my policy would not be optimal. So for optimal policy, this will be fulfilled. And surprisingly, mathematically, there is a proof that this policy always exists. This policy always exists under some assumptions, of course, but that's the beauty of the mathematics here. So, and that's exactly what I would say. Let's say we have, it would be, in this case, very easy to move in this labyrinth if we have something like that. -7, -7, -8 probably, and so on. Because in each state, we will clearly select the where to move according to the neighbors. So if we see that this one is -6, where we'll move from -7, of course we will move there. That will be optimal policy pi that we will pick. So that's actually the algorithm. It's all greedy algorithm in general. So you always select the action that moves you to the highest value. Always do that, and in this case, you will have optimal policy. Right? So. Now there is a couple of assumptions I would like to actually say that we assume that agent observes all state, and again, we don't have a history. We don't make our decision based on the history. So we know that if we know this value, we know them, but we are not using our decision based on this history. And also, again, there is a very strong assumption. First of all, that we can store everything in these tables. Because you see, if we have multiple states, multiple actions, Like the table is getting larger and larger and larger. And also that in this case, we assume that we know all probability. All this P function knows completely. And this is quite often is not true. And that's exactly where we'll see reinforced learning acting very cool. So in this case, optimal policy. And yeah, so that would be always pick A to go for highest allowed for this particular thing. So it's usually called that your action, let's say taking action, would be argmax of all possible actions in S for this policy. Yeah. How we calculate these numbers, you mean? Or yeah, that's again, next slide. That you don't have that. You just know according to the rules that you get a -1 all the time. Like if you get a step, you have no idea. It would be a dream to have that. And that's exactly what these reinforced learning algorithms are doing. They're trying to build these things, and you will see that. So, and that's exactly where we stopped. Let's say this is a terminal state, and you can move left and right. And let's say that let's say you know values here. Let's say it's maybe 5. Here the value is, I don't know, 6, because the rules are different. Maybe we can jump. Maybe it's like they're not in this particular left or right easy way. And let's say here we have a 3. Considering that you know that from here you can move here and here with some rewards, with some penalties, can you get this number? If considering that we have some cells, so already with the numbers, with already this V, so this is V for this state. Let's say this state 0, 1, 2, 3, 4. So this is V0 for the state 0 is equal 5. This is V for 1 equal to 6. And we are asking what would be the... Can we find it? And there is an absolutely amazing theorem called Bellman equation that says, yes, by knowing where we can move, we can get the value of this particular thing. So for the deterministic environment, it's actually quite simple. It's just for the specific policy, it's maximum of the actions considering the reward that you get immediately, because this is RSA. We're right now in the state S. And let's say right now from the state S, we can move left or we can move right, right? So what we are looking at, what reward do we have? So let's say for this motion, we will get reward 7. And for this motion, we will get reward -5. Just randomly. The system knows that. We have no idea, but that's what we get. And therefore, our value would be, so we have two options. So we have for left, let me just write it in a different ink. So what we have for the left, we have 7 plus discount, but let's consider that we do not consider discount right now, for 1 multiplied by the value of the next state. This is the value of our next state. Therefore, we actually multiply by 6. That will be for the left motion. For the right motion, what we will get our reward -5. We will get penalized, plus, again, let's say 1, multiplied by the value of the state number 3. And therefore, here we will get reward 13. And here we will get reward equal to -2. And therefore, if we take the maximum through these actions, what would be the value of 2? Will be exactly 13. So knowing the values of the neighbors, we can calculate the values of the each individual state. And this is a beauty. It's a mathematical beauty because it allows everything to work. So knowing state value function of some states, we can derive value function for a known state. And in this case, we can even say that sort of our stars, our optimal, what we will describe in this case, we will say you remember pi star as optimal policy. So this is just another way to say that I'm just not writing pi star here. So our value will be the maximum of all values for the specific state in action, and here is the same. So the agent must always select the highest action value, and that would be a strategy that helps us to maximize our return. That's important to know. Technically speaking, if we look at I guess it's right. So we always, so right now again, the thing why this specifically formulated, because we assign some states like 5, 6, now we know 13, 3, and t. So now the question is where to move. And the strategy says that agent must always, for optimal strategy, for the optimal policy, always select the highest action value. So in this case, again, that's exactly what we did. So we need to move left. Okay, this is actually, we simplify the things because we consider only deterministic cases. When we press right, we move right. So in example with the squares and circles, remember there is still probability to maybe not move or move with another rewards. So this is official, it's general equations, and they're extremely simple. Again, from if you look at especially at the values, we just do summation over all actions with our specific policy, and we just, again, in the brackets, you see the still reward multiplied by that. So I just simplified for you because this is a Bellman equation in general. Okay, that's really cool to have it. So now the question is how to get numbers. How to get these numbers? It's quite a tricky question because we actually know them. We don't know them at all. And let's consider the classical example of this sort of maze. This is terminal state, and I'll probably not do that. This is terminal state, and this terminal state. And we would like, right now, assume our policy to be random. We assume that our policy is just, so we completely randomly pick direction. That's a fixed policy right now. The question, how we can find the numbers inside of this grid. First of all, what we are doing, we're actually assigning zeros to the terminal states. Terminal states always should be 0. And then, that's magic. We absolutely randomly initiate all other numbers. So let's say what I'm doing right now. I say, okay. Usually it's 0 point something, it's close to 0, but I will do it a little bit larger. I would say 1, 2, 3, 6, 2, 1, 9. Let's say 2, 2, 1. It's hard. 5, 4, 3, 3. This is just random generation that will not satisfy the criteria for the optimal V for selected P. It doesn't really make sense. It doesn't satisfy any equations right now. It's just random. And that's the magic what's happening right now. I just look at every square and calculate it from the neighbors. We know that we can do that. Remember, we did it already. So I just calculate this number from the neighbors. And in this case, considering our policy is random, and let's say we have -1 reward for each movement, for any movement we have -1 reward, what would be the value in this case here? We will get 9 plus 9 plus 2, actually we'll get 10. And we update this value. And then we select next square, already with a 10 here, and repeat this. And surprisingly, this always converges. It always converges to the final so-called Q matrix. No, it's not Q matrix. To the final solution. So in this particular case, since this is a classical example, what we will have something that look like that. After a couple, it's called sweeps. After sweeps through that, couple of sweeps, what we will get, usually you need quite a lot of sweeps. So you update these values based on the neighbors, and it will always converge. And what it will converge, it will converge to this matrix. Do you have, can you explain the meaning of this number, sir? Do you see the meaning of this number? No, just like, what is minus 18 in this case? Like, considering the problem that we're right now looking at, what would be that? I don't know, physical, but like what's the meaning of minus 18? It's better than minus 20, but exactly what is it actually? Minus 18 is better than minus 20. It's absolutely right. You actually see that if you go far from the terminal states, you get worse. But in general, what does it mean, considering that we have a policy? Negative what? Okay, I will give you kind of all around the correct answers. I'm asking you the following in this case. If I start with the state, with the state, you see it. On average, how many steps do I need to go to the terminal state? Considering the policies that we have, our policy is this one. We are acting in a policy. How many steps do we need in this case from the state? On average. Of course, sometimes you go up, and you zero. But you can imagine you going like that. On average, how many steps? Come on. 20. That's a value. Each step penalizes you for -1. So on average, from this stage, you need 20 steps with this policy, random policy, to reach one of the terminal states. And if you run actually simulations, basically naive simulations, you will exactly get these numbers. But we got them from actually reinforcement learning, from these Bellman equations, from this update. And that's the beauty of that. So right now you have a matrix. Of course, we know this policy is not optimal. You can really create you know what the optimal would be like. It will be some -1s around the terminal states, because you always, in optimal policy, what you actually want to go here and not randomly. So therefore, for this particular policy, we have this V states. So on each state, we have a number that's called state number. Okay, so we found it. It's stabilized. We cannot improve it more. So this is our numbers. What we can do next? We can do next so-called policy improvement. Now we decide, okay, let's update our policy. We see that this absolutely stupid approach doesn't really optimal. And a policy improvement is to create a new policy, pi prime, that always take the maximum direction. So it always goes to the maximal numbers. And in this particular scheme, let me. I don't want to. Do I have? Oh no, I don't have this nice. I think if we have this matrix here of the states, what would be the direction from 18? -18 from this? I'm always select right now my action. Before that, my actions were random. Now I, for each state, want to define specific action. What would be the action from -18? Okay, let's say from -14. What would be the direction? Yeah, left. So that's my policy. Now my policy say that pi prime at this, let's say, I will do that 1, 2, 3, 4, and so on. At the state equal to will be 100% go left. You see, we update the policy. Now, let's say we go here. For instance, what would be the policy? Go left as well. And we can repeat it and repeat it again. So do we have any problems here with that? So at the end, what we're actually drawing, we are drawing our policies like that. So from here we go here, from here we go, and here, in some cases we don't really care where to go, because let's say we have a -22, and minus 20 and minus 20. In this case, we have 50-50%, so we just randomly select. So in this case, the policy for this state will allow us with the 50% to go left and with 50% to go right. Okay? Is it more or less clear? Cool. So, do we have some trick here? No, we don't have any tricks here to show. Therefore, we now have a new policy. Does it mean that we solve the problem? So what we can do next, we can do this policy evaluation again, but assuming new policy. So right now, we can assume this policy that we just derived and do the cycle policy evaluation again. Actually, if we do it right now, what we will get, even with a random initialization, we will get minus 1, minus 2, minus 3, minus 1, minus 2, minus 3, minus 4. Let me just finish it, minus 2. Can we improve it more? Can we come up from... 4 is wrong? Yeah, it's 2, of course, yes, sorry. Can we improve it? Now, my task to go again to the policy improvement, to look where we can move from each of these positions. And if you look at here closely, you will see that there is no improvement. There's the same policy, and therefore we find the optimal values and optimal policy, and we cannot improve that. And that is a theorem that says that that would be optimal policy for any case. So the fact that our cycle stops here means that we find an optimal policy and optimal values. There is no improvement. In many cases, you need to repeat the cycle multiple times, 10, 20. In what we will see, it's like a million times sometimes. So it's really sort of it's an iterative process. And this is kind of policy iteration, so-called policy of iterations, or in some cases it's called general policy iterations. So what is happening? So first you get your V and you update your pi. Then based on this pi, you update your V. So this is called policy improvement. Is it called policy improvement? Yeah, improvement. And this is called policy evaluation. And by doing this loop, it will converge, and it will converge to optimal policy, to our pi prime. And that is a kind of, right now, what we need to think about, if we talk about this particular thing, what we need to see is that we did this, we get not lucky, I didn't finish it, but in order to stabilize our solution, we run this swipe, let's say 10 times in order to get the numbers that we have here. And only after that, we update our policy. What we can do, we can just run swipe once and update the policy. And again, then swipe only once. So we do not wait for stabilization. It will surprisingly still work. So in general, the task of reinforcement learning, it's to combine this iterative process in a different manner. So we can iterate first. Again, we can go through all the possible sweeps until we stabilize, then update our policy. But we can update our policy after each second sweep, for instance, and so on. And in general, in this case, the process when you at the beginning have policy 0, then you get, after evaluation, you get your numbers. That's what we did for this particular policy. Then you get a policy 1, and this is improvement already of the policy. Then we get it pi 1, and this is again calculations and so on. So this cycle can repeat, but we can actually do it in a different steps. So we can, again, do not wait for whole cycle to end. We can just update our policy after only one sweep. And in this case, it's called value iteration, and this is sort of what's happening. So this is our it's V, and this is our policy. And we just jump between two things, between two lines. It's harder to explain what is greedy in this case, but policy is called greedy when it goes always make the select the action with the maximal value. next to it. So it's called greedy policy. So therefore, and our optimal policies and optimal values are actually sort of, our optimal policy is by definition greedy. So therefore, by doing this cycling, you eventually will converge to one point, and that will be your optimal policy on this maze. So you first of all will be able to create these numbers in your maze that you asked about, and also you will have a specific policy how to move in each particular state. Oh yeah, it's longer than. So, but we will briefly go through that. In this case, it's like 10 minutes, probably max. But problem that we do not have the P in real life. Right now, we saw how to build this probability thing. Then we have the probability of S prime R from S and action. But we, of course, don't have that. We really have no idea how it works. So therefore, we need to use so-called model-free approaches. And that's how reinforced learning is based on. So what you saw before, it's mathematics. It's basics that explain why these methods can work. But that's what you see in real life. So you have the reinforcement learning algorithms, and they can be model-based when you actually know the environment. And for instance, when you play Go, you know the rules. You know exactly what you have as a penalty because you know the rules. So you know all this P. It's given the model. You can learn the model. You can learn this physics process of this. But in many cases, you do not care about that. What you're doing is model-free reinforcement learning. And in this case, what you can do, you can focus on optimization of the policy. And this is a policy optimization methods, multiple of them. Or you can go so-called Q-learning. And Q is the same Q that we saw before. It's these Qs, these values. In this case, it's not state values because you cannot actually do Q-learning on the state values. You can do this state action pairs. And one of the, and Q-learning is the basic sort of umbrella term. And this is so-called deep Q networks. And that's when the beauty is. So in general, again, this is what we can learn: policies, value functions, action value functions, or environmental models. That's a scheme before. So we are doing most often is action value functions, and this is called Q-learning. And the system is quite simple. You go through your, because right now what you're doing, you do this steps by steps arbitrary, more or less, and you learn these Q values. So right now you don't have probabilities. Your agent just take a step and try to create the picture what Q value for this state is. And you sort of, it's very simple. So every step, what you're doing, you update your Q as the old value, so or current value, multiply by some learning rate, of course, as usual, plus what you expect from the future. You see, it's a reward for the, it's very similar to what we saw before, absolutely the same as the Bellman equation, discount factor. And this is estimate of optimal future value. So what we will get in the future. And then you just sort of do that iteratively by exploring your system with your agent. And again, in this case, this is how it looks like. So, so for each episode, we initialize our states and loop for each step of the episode, choose action from the state using the polity from Q. So we have a policy, take action, observe what we get, and update your value. Move to the next steps and do it over and over again. And until you reach the terminal point. That's the algorithm itself. The problem with that, yeah, nice. It's very, very fundamental issue. So imagine this is a task. So if you reach the coin, you will get, let's say, +2. If you get the Princess Peach, you will get +10. Here you have with the Bowser -100. And each step -1, as usual. So you do this -1. And of course, your task is to kind of, and all the states are terminal. So, and you imagine that we can move only up and down. So in this case, what we can do, we can draw this things again. And now I will do the following. Right now, I initialize everything with zeros. So my agent knows that everything is 0. All values are 0. All Q values everywhere is 0. And of course, for each cell, we can say there are 2 of them because it's right or up. And now we randomly, because everything is 0, we can choose randomly. We choose go right. So we go right. And therefore, what would be the state after we go in right? We have a reward of -1 And imagine that our learning rate is 0.5. So in this case, when we move from here to here, this value getting dropped to minus 0.5. We make a decision, we go right, we see 0 here, and we have a reward of -1. So we have minus 0.5. See, clear? So here we, again, let's say we decided to go right as well. We go right and ba-bam, we have +2 because we get reward for this terminal state. So what will happen with this state in this case? We go right, we get -1 and with a discount with a learning factor of 0.5. So we have minus 0.5 plus 2 plus reward that we get. So this state right now is, well, I will do it red, is 1.5. So now we start again. We reach terminal state. Our episode ends. Now we're going up. Now we start again. What we have, we start again here. Let me draw it again. It's a second iteration. Where should we go from the left one? According to our policy, we always move to the highest, the thing that will give us highest values. We go up because we have a minus 0.5. Yes, okay, so that's right. I see that to confuse. So what you're doing in this case, you are going right as well, because you're, come again? No, you are going up. Why are you? No, you have a minus 0.5 right now. You're looking at your actions and you choose maximal action, so don't confuse me. So you actually, in this case, this is better. So you go up, right? So you go up, again, what you get, absolutely the same minus 0.05, go up again, and now you get to this value. So it will be, this is still 0 because it's right, we don't care. What will happen here, when from here we go to the pitch, we'll get +5. Did you get it? So it's very similar to what happened here. Well, +5 minus some penalty. So we have a big plus in general because we reach the terminal state that gives us +10, right? What will happen next? We right now have this. Yeah, it will be 9. Yeah, I just didn't want to calculate, honestly. So so now we have this particular state, terminal, and we have, so I start from the left. Where to go? Right now, again, I do it randomly and so on, but eventually what I will start to do, because this 9 will propagate here. Do you see it? If I will go right now right, I will get in this particular cell, I will get minus 0.5 multiplied by 0.5, it's alpha, minus 1 reward, plus 9 multiplied by 0.5. This is alpha multiplied by this, what I get. So my cell on the top, this one, will actually have 4.5 or something similar, minus 0.5. And then after that, when I map that, I will always go up. I will always go to the optimal solution because this is optimal solution. This is optimal. We learn everything. Fine. Everything works absolutely magnificent. Do you see problem? But we already went there and we checked that it's not doesn't worth it. But the problem is very similar. Yes. What will happen if I will switch position of the pitch? We already know what will happen if we move right. So what we'll have if I just draw this one, we will get at some point minus 0.5. Yeah, we will get 0, 1.5, and we get a terminal. Next time I will go here, and I will be in this state. I have no idea why should I go up, because up I get 0. Right, I will go 0.5. So I will always go here. I will never go up because my weights tell me that. And that's the biggest problem in reinforced learning. It's so-called exploration with exploitation. Right now, what we are doing, we're exploiting the known values. So we always go to the highest value. Unfortunately, in this case, we can keep some squares unexplored completely. And therefore, it's very important, and this is algorithm, to at some point when you select action, do not go to the highest action, but with some probability epsilon to choose random. In this case, it will allow us to explore. And usually this epsilon, it's called epsilon greedy algorithm, it's getting smaller and smaller because at the beginning we want to explore, we do not want to stuck, we want to go around this grid in order to learn. And then when we already learn enough, we start to decrease this epsilon. And this is extremely important thing for the for these things. So this is a Q-learning again. Yeah, I don't have time to go here. So the idea, unfortunately, this is the most interesting part, but maybe this part I will it's 15 minutes more. I will do it the next lesson, because that's right now you see no connections to these deep networks. You are doing these optimizations, you are doing these policies, right? There is a very beautiful connection. That's why it's called DQN, because what we will do, we will use supervised learning to, like right now we have this Q table. Q table, it's this things that we know everything. And we, based on this Q table, we go to the highest neighbor. We will replace it with a neural network that will be retrained every step. And that will allow us to learn of very complex relationships and very complex algorithms, because these algorithms, like Q-learning, can work for this particular example. This example when you try to keep your road on the cart, because it always wants to drop, and you have left and right control. So you need to balance it. So you can do it with a Q-learning or with deep Q network. And we also, during practice, we will solve this problem with I think, okay, not on the lecture, I will do it in practice. It will be 10 minutes on the practice. Just again, you see this 5 slides, but I don't want to just jump through them very fast. Okay, on that note, with this Mario game, the balance between exploitation and exploration is extremely important. And yeah, that's when we will pick it up and just introduce DQNs next time. Thanks a lot. Whew.